Dear students, this is a PPT presentation prepared by Anoop Thomas, Ronnie Anthony and Boniface PL of EC Department, Asst. I will be presenting Module 4 of Computer Organization for S4 EC students under KTU. In Module 1 to 3, we have already learned about the basics of computer organization considering MIPS as an ensemble architecture. In Module 4, we will be learning to implement the architecture using different hardware blocks, which is technically known as microarchitecture. The two major topics that are discussed in this module are microarchitecture design process and the different types of MIPS microarchitectures. In order to understand the basics of designing process, we need to understand what is an architecture. We have already seen the different levels of abstraction for an electronic computing system in Module 1 as shown here. Our current concentration in this module is on the microarchitecture which connects the architecture layer to the logic layer. The architecture here is defined as the programmer's view of the processor in terms of registers, instructions and memory. There are different architecture variants like MIPS, x86, PowerPC, etc. We have been studying MIPS as an ensemble architecture in this subject. The point to be understood here is that a single architecture like MIPS can have more than one microarchitectures. The logic layer in the diagram represents the implementation of microarchitecture using digital logic blocks like adders, subtractors, comparators, memory elements, FSMs, etc. Okay, so in this particular slide, we will be explaining a little bit more detail about microarchitecture. So we have already seen that your microarchitecture acts as an interface between the logic layer and your architecture layer. Okay, so that's the position of your microarchitecture layer. Now, what do you mean by microarchitecture? Technically, your microarchitecture can be defined as a specific arrangement of registers, ALUs, FSMs, memories, and other logic building blocks needed to implement an architecture. It's basically an arrangement. Now, whenever you have an arrangement, you will have different choices of it. And whenever you speak about engineering, the choices will be based on certain trade-offs. And here, automatically, the engineering trade-offs associated with this will be performance, cost, and complexity. So we will have different microarchitectures which are decided based on these trade-offs. The point to be understood here is that all the programs or the instructions which you are using in MIPS will be implemented. The program stuff doesn't change. The top part, the top level programs or instructions won't change. It will remain the same for the different microarchitectures. But the microarchitectures or the internal designs can be different. So as we have seen from the earlier slides, we are trying to design microarchitectures. So in order to understand the designing of your microarchitecture, we need to understand what are the components which are there in the architecture which is going to be implemented as a microarchitecture. So the architecture in a designer perspective consists of two things. One is the instruction set, the other one is your architectural state. And the instruction set is something which is fixed, and we have already seen the instruction set as part of your module 2 and 3 in detail. So that's something which we have already seen. Now the second one is your architectural state. Now what do you mean by an architectural state? So the architectural state for an MIPS processor consists of the program counter and 32 number of 32-bit registers. That means we'll have 32 32-bit registers and the program counter. This whole together is called as your architectural state. Okay, so we are going into the designing of your microarchitecture. So you need to understand what are the major design process which are involved in your microarchitecture. So we divide your microarchitecture design process into two types of designs. One is called as your data path design, other one is called as your control design. So you'll have to design a data path and you will have to design a control unit. So these are interfacing, interacting parts. They interact with each other. That's how you form this particular microarchitecture. Now your MIPS basically has a 32-bit database, the data path, and as the name suggests, it basically deals with the data. It has a 32-bit data path which basically deals with data. And it consists of memories, registers, ALUs and multiplexes. These are the structures which are used as part of your data path. Now the second one is your control unit. So the control unit is based on the current instructions and it tells the data path how to execute the instruction, using different control signals like much select, register enable and memory write signal. So that's how your control unit works. So combining both these things to interacting parts, you will have your microarchitecture. Okay, so we are starting with the design process. We have already seen that what an architecture is. What are the design design process which are there, the data path design and control unit design. Now we need to understand what are the elements which are involved in your microarchitecture design. So from this particular slide we will be speaking about the elements. It's basically called as state elements because it is associated with your digital design using your finite state machine. So that's the basic design approach that is going to be followed. That's why it's called as state elements. Now in our case for your MIPS processor, it basically consists of three different state elements. It is basically your memories, your program counter and your registers. These are the three things, or these are the three state elements which are associated with your MIPS process. So we have just represented that using diagrams. So as you can see, you have two types of memories called as instruction memory and data memory. Then the registers are situated in your register file, and then you have a special register called as program counter. So in the next slides we will be explaining each of these particular elements in detail. So the first element, state element that is to be considered is your program counter, and it is one of the most important elements which is there in your MIPS processor. So the program counter is defined as a 32-bit register which holds the location, that is the address of the current instruction being executed. The important point to be noted here is that the program counter is holding an address value, and as you can see in this particular diagram, you have 32 bits as input and 32 bits as output, and you have a clock signal which is basically your timing signal which is used to produce your outputs according to the timing requirements, and it is given as PC dash at the input and PC at the output. Okay. So while the current instruction is being executed, the program counter will be incremented to point to the next instruction to be executed. So during the execution of the current instruction, the program counter will be incremented depending upon your clock pulse. So that is why the output is PC and the input is PC dash, and your incrementing can be either +4 or other values depending upon the instruction that you are trying to execute. That means if it's a jump instruction, it can take other values than your PC +4. So that's the idea of your program counter. Okay, so the next element that is going to be a state element that is going to be considered is a memory element, and it's called as instruction memory. And instruction memory is basically a memory which holds the instructions or the programs and has a 32-bit address input and a 32-bit data output. So the data output is associated with your RD port. It's called as read port, represented by RD, and address again is 32-bit. It is represented by your A port. So you give a address value to this particular memory, you will get your corresponding data value. So it's basically a single read port. You have only a single port through which you will be reading your data. So that's the idea of your instruction memory, and it stores the instructions of the program which is going to be executed. Okay, so the next state element that is going to be considered is your register file. So the register file is basically a state element in MIPS architecture which consists of 32-bit registers. So in MIPS architecture you have 32-bit registers. So that is stored in a element called as register file. So this register file consists of two read ports, that is represented by your RD1 and RD2, each of 32 bits, and it has through this particular ports the register contents can be read. Through these ports RD1 and RD2, the register contents will be read by mentioning the 5-bit address in A1 and A2. So you have 32 registers, so automatically you require 5 bits to represent these 32 registers. From the concept of 2 raised to 5, you get 32 registers. So using your A1 and A2, which are basically 5 bits, you will be able to get data in RD1 and RD2. So as you can see, you have two read ports. You have two read ports through which you can read the data parallelly. Now, now coming on to the write operation. So it's basically a memory which can be read and written. So you have a write option as well. So in a write operation on a register, a write operation on a register can be done by providing a 5-bit address in A3. A3 is the port which is associated with your write operation. So in your A3 port, you will be giving a 5-bit value, the address value, and the data to be written. So since we are doing a write operation, we have to give data as well as address. So you have given address in A3, and the data to be written will be provided, which is all, of course 32 bits, will be provided in the WD3 port, which is again a 32-bit port, write data port. That's your WD3. And along with this, we need to also give an enabled signal called as a write signal, and this particular write operation happens along with a clock signal. So it's a clock synchronous to clock. So you need a clock signal, you read the write enabled signal, and you need to specify the address value in A3, and you need to give the data in WD3. All these things are given, your write operation will be performed. So again, in a design perspective, the thing that you need to understand is, in order to design the register file, we have considered the R-type instruction. That is because this particular instruction has the maximum number of parallel register access. It will have in a MIPS environment, the R-type instruction has the maximum number of parallel register access. That is why you have 3 ports, 2 ports associated with read and 1 port associated with write, which comes from the R-type instruction, which can take 3 different register values. So that's the design criteria which has to be understood. Okay, so the last state element which is going to be discussed is your data memory. It's again a type of memory, but as the name suggests, it is going to store data. and again it has a single read bar write port. It has a single read bar write port, so you have a reading option as well as a writing option. So when you go for a write operation, when you go for a read operation, you give the address value, 32-bit address value at the A port, and you will get the data value through your RD port. So it's again 32 bits. So that's how your read operation read operation is performed in a data memory. And when it comes to the writing, it is given, it is done by providing your address again at the A port, and your data in your WD port, the write data port, again 32 bit, providing your write enable signal WE and the clock signal. So similar to your register file writing operation, it requires synchronization with respect to your clock and a write enable signal. So when all these things are given, the data which is given in your WD port will be written into the address which you have specified in your A port. So that's the basic working of your data memory. Okay, so in summary, with respect to your state elements, the two important points that you need to understand is, one is all the state elements, the write operation is sequential. That is, it is performed on the rising edge of the clock. So it is basically a sequential operation. Whereas your read operation is combinational, and all the read operations are performed combinationally. So write operation is sequential, whereas your read operation is combinational. Okay, so there is no clock getting involved in your read operations, and you have a clock coming into picture in your write operations. Okay, so we have concluded the state elements. Now we will move on to the different microarchitecture types. We already seen that MIPS can be implemented using different microarchitectures. MIPS is the architecture which is implemented using different microarchitectures. So in our particular syllabus, we are concentrating on three types of microarchitectures called as single cycle, multi-cycle, and pipelined. And out of which our focus is mainly on single cycle and multi-cycle type of microarchitectures. Pipeline is just given as a introduction, or just a briefing of pipeline is given, but we are concentrating on single cycle and multi-cycle based microarchitecture types. So the first type is your single cycle. The idea here is it executes the whole instruction. That means the MIPS processor takes one instruction, then executes it. So in the case of single cycle execution, it executes the entire instruction in one cycle. That is the design criteria for single cycle microarchitecture. Automatically it has a very simple control unit. We have already seen that we have designing of control unit and data path. So when it comes to single cycle, it will have a very simple control unit, and it does not require any non-architectural state. We will be defining on this particular stuff in detail when you explain single cycle microarchitecture. So we'll explain it later. Again, the cycle time is limited by the slowest instruction. So that is because since you are having a single cycle, the clock frequency will be, or the cycle time will be decided by the slowest instruction, because you are giving the same clock cycle or clock to all the particular instructions. So the slowest instruction will decide the cycle time. So that's the drawback of your single cycle. The next kind of microarchitecture is the multi-cycle microarchitecture, which again executes instructions in a series of shorter cycles. So you have different number of cycles associated with a single instruction. So again, simple instructions, as you could automatically assume, will be executed in fewer cycles than complicated ones. The hardware cost can be reduced by reusing your expensive hardware blocks. We will see how it works later. and a multi-cycle processor executes only one instruction at a time, but each instruction takes multiple clock cycles. So the output of the process of one instruction at a time remains as such, but the instruction can take multiple clock cycles. That's your multi-cycle microarchitectures. Finally, you have something called as pipelined microarchitectures. Again, that is not something which is focused in the syllabus. So it is again applies pipelining to the single cycle microarchitecture. It basically executes several instructions simultaneously, so that improves the throughput. Until now it was single instruction. Here you have several instructions being executed parallelly, so that's increasing the throughput. So that will have additional logic. There will be a lot of dependencies between the executing instructions. Again, it requires additional registers to implement it, so it's quite complicated compared to the other two types of microarchitectures. So these are the three types of microarchitectures. So until now, in the first part of this particular series of your module 4, we already understood the basic design process involved in MIPS microarchitecture design, and also we have seen the different types of microarchitectures as part of your MIPS process. So in this particular slide we will be speaking about the performance analysis, because always when it comes to engineering we are focused on the performance of our design. Now whenever you speak about performance analysis of a processor, you should be aware that process performance will always be associated with execution speed or execution time. So the execution time should be reduced, or the execution speed should be increased. So so the performance analysis here is defined in terms of execution time, and is given in terms of an equation. Execution time here implies the execution of a program, execution of a set of instructions. What is the time that is required by the processor to execute a set of instructions? That is called as your executing time. That will automatically be dependent upon the instructions which are there. If you have a program, it will have a number of instructions, so it will always, the time will always depend upon the number of instructions. That's your first factor, the instructions into something called as cycles per instruction. That means the average number of clock cycles which are required for an instruction to be executed in MIPS. So that is called as CPI. It's called as cycles per instruction, the number of cycles for a particular instruction. Okay, an average value, and it is the reciprocal of throughput. That means the throughput is the instructions per cycle, the number of instructions which are executed in a single cycle. That's called as throughput. So the execution time, which is considered as the performance analysis, is given by instructions into CPI, that is your cycles per instruction, into automatically the clock frequency, that is your seconds per cycle. So that gives you cycle goes off, instruction goes off, and finally you get it in terms of seconds. So that is what you mean by performance analysis in terms of your processor. So the number of seconds per cycle is the clock period TC. So when you calculate it, you get the execution time, which gives the performance analysis of the processor. It's a generic term, it's not depending upon MIPS. Any processor will have the same method of analyzing its performance. So that concludes the first part of this particular module 4. We have stopped with the performance analysis. The rest of the topics will be taken in the next session. Thank you for listening.